Now the next question you have in mind probably is what should I have as target, which parameters should I follow, and so on. And my key message here is that the water stream cycle chemistry is specific. It depends on the circuit design, and one size does not fit all for sure. And what we see typically is that when we see on our review, it's typically copy-paste of standards without taking into account the specificity of the plants. And that is really important to answer a series of questions to determine the best strategy. What is my boiler design? What is the metallurgy in it? What is the cooling system, the drum pressure, temperature, attenuation, discharge limits? I will end this question with a case study. You can see here it's pictures of an inspection Laborelec did in 2009, and what you recognize here is the sign of several location that is found in the air-cooled condenser inlet and outlet. And this really linked to the bad choice of target pH of treatment. We have recommended to increase the pH from 9.6 to 9.75, and the inspection we did a few years ago has shown that the situation is improved already. Based on the review of the chemistry, we have concluded that it was possible for the plant to increase the target to a pH of 9.8, and that will further improve the situation that we will see in the next inspection. And so this ends here the first topic, and we are now open to receive all your questions.
Thank you. Any questions? No? Okay, in which case I will ask you a question. Could you tell us what the best treatment strategy is to control the flow accelerated corrosion?
Yes. Thank you for the question. This is a question we have a lot on when we review power plants. The point is that flow accelerated corrosion is a peculiar form of corrosion, which is a combination of the flow, choice of materials, and chemistry. I will maybe let my colleagues from the material side to comment on the material choice and design parts. For the chemistry, finally, is the only thing that we can really control during operation and impact on this form of corrosion. And the two measure parameters is really the pH and the oxygen level. So the oxygen, we talked about that already. So for flow accelerated corrosion, it's very dangerous to have reducing conditions. That means a situation where we don't have any oxygen at all, because the oxygen will help to replenish the oxygen layer due to the flow corrosion. And the pH is also important, and to have the sufficient target pH. The measure issue is that we need to have a pH above 9.8 to protect against corrosion. If we do the treatment with ammonia, due to the difference in volatility, ammonia will tend to stay more in the vapor phase than in the water phase. And so the case we have seen in the air-cooled condenser, it was due to the fact that in the first condensation zone, the ammonia, there will be a deficit of ammonia in the first droplet that will form. And so there is a risk there to develop flow accelerated corrosion. So it's very important to maintain sufficient pH to protect everywhere in the circuit, both the water and vapor phase.
Thank you very much.
Yes, regarding material, of course, the chemistry is the first aspect to treat when there is a risk of flow accelerated corrosion. If you have optimized your chemistry, you can also work on your material aspect. By increasing a little bit of the chrome content of your material, you reduce the risk of FAC. It's also important to know that we already observed that sometimes we just use the good material but not the good filler metals, so for the welds. So it's also important to have this higher chrome content for the welds, and to reduce as much as possible all the rugosity, roughness, and the design to create the turbulence that creates as well and increase the FAC risk.
Thank you very much, Sylvie. Yeah. We will then pass on to the second question. As there's still no questions, so don't hesitate to ask us questions while the speaker is presenting via the chat, and we will address them at the end of the specific thematic that is addressed. So the second question for Anne still is there a monitoring strategy in place for the water steam circuit?
Yes. Thank you. To introduce the importance of monitoring, I would like to introduce another concept. Actually, it's the concept of chemistry maturity. And this is really based on 3 major pillars. So the control of the treatment and purity. So we just discussed about it in the first topic. The monitoring, because you need to be able to monitor continuously data to follow your chemistry and to know what is actually happening in that. It's the only way to develop a proactive and predictive approach and to be able to react on time. And to react, that means to know what is the target I need to keep during the water steam cycle, in the water steam cycle chemistry, what are the alarm levels and the course of action depending on the level. And this is really all the approach of alarm management. And this really all this integrated approach that has to be perfectly managed, that will lead you to increase the chemistry maturity and to lower the risk of incidents. And this is really what we strive for when we support the plants through a review, supporting the plants to achieve this chemistry maturity. And so that's brings us to the question of monitoring. There is a need for minimum key level of instrumentation to be able to follow the water steam cycle chemistry. And what is this key level of instrumentation? So let's remember, we talk about 2 important targets for the water steam cycle chemistry. Those were the treatment and the purity. For the treatment, we talk a lot about controlling the pH. Indeed, the pH is the most indicative of the water steam cycle chemistry. But actually, there is another parameter which is even more reliable to control the treatment and chemical injection, which is the specific conductivity. And the second point is the purity. The major parameter to monitor and follow your purity is the cation conductivity. Through this measurement, it is really sensitive and will be able to detect any impurity ingress in your system. Then there is the dissolved oxygen, very important for the corrosion, and the parameters that the silica and the sodium. So online is key to follow the water steam cycle chemistry. What about offline measurement then? It is required to do comparative measurement, such as pH, specific conductivity, silica, and in case of troubleshooting or diagnosis where you need to have additional parameters to better understand the situation. And then once again, I will end this second topic with a case study. You can see here, it's the pH control in one of the plants in the feed water. What you see in gray, it's the control bands, which is the target pH for them. You can see that they do the ammonia injection actually based on measured pH. And you can see here that's what's the measured pH seems to be really in line with the target pH, and everything seems to be very good in terms of chemistry control. But if you look to the calculated pH, which is calculated based on the specific conductivity, which is more reliable and more representative of the treatment, you can see that all this time they were actually below the target level with the consequences we can imagine. And this was due to the fact that the plant was equipped at the design with a pH analyzer with a probe that was not appropriate for measurement in ultra-pure water, because measuring in ultra-pure water is a difficult exercise. So the first thing here, the first message I want to give is that short-circuiting the monitoring to save money at design phase is usually not a good strategy. You can save maybe a few thousand, such as in this case, but if something goes wrong, I can assure you that the cost is much higher than that. And the other point is that chemical injection, chemical treatment is so important in terms of strategy, and so it is really essential to base it on reliable parameter. And so this ends this topic, and we can move on to the Q&A session.
Thank you again, Anne. We have 2 questions from the audience. So the first one, when I left classical production in 2016, CCGT, there was a tendency to increase oxygen. Here at Doel, this is not the case yet. What is the strategy for the future in nuke?
I think that this question is really to the difference between all volatile treatment and oxygenated treatment. And indeed, in oxygenated treatment, we are going to strive for high oxygen level. And this really links also to the fact when I mentioned the role of oxygen. So normally the oxide layer is a magnetic layer, but to the presence of inclusion of hematite layer, which is formed by high oxygen level, will increase the oxide layer. So oxygenated treatment has been associated to better control in terms of corrosion, and we have indeed seen a reduction in terms of iron transport. But the presence of oxygen will impact corrosion in presence of purity. So in this kind of treatment, it is even more important to strive for very pure system. And so typically, I think in this case for CCGT, I understand this kind of choice because there is higher risk for flow accelerated corrosion due to the heat form of heat transfer. And typically in this kind of system, they have condensate polisher installed and so on. And so the purity control allows to go for that kind of treatment. But yeah, it's really another form of treatment, and especially there, one needs to be very careful in defining the alarm monitoring levels to correspond to best standards.
Okay, thank you.
And especially there, the startup and shutdown is very quite complex, and maybe I can let one of my colleagues to comment that on the startup in oxygenated treatment.
Yes. I have one quick question for the rest.
Oh, yes.
We have 1 minute left and another question open from the audience. Sorry about that, guys. What is the advantage of having an online chlorine analyzer? Is it required along with sodium analyzer?
So I would be very curious if you have an online chloride analyzer, which is really reliable. I think that sodium analyzer is good and sometimes even more sensitive in monitoring the purity, especially if you have a seawater cooled condenser. But chloride measurement is quite difficult, sensitive, and it's difficult to achieve the same accuracy in terms of online analyzer. And so I think that for the moment, the best strategy is still cation conductivity and sodium analyzer to monitor the purity.
Thank you very much, Han.
Yes.
I think we will pass now on to the next expert speaker. And once again, thank you very much for enlightening us on that subject. Our second speaker is Marnix Vermeersch. Marnix, thank you for joining us. And the first question he will answer is, does the monitoring strategy focus on the right aspects?
Yes, hello, good morning, everybody. So power plant chemists typically apply standardized monitoring programs, and that are in fact derived from international standards. And most of those standards are imposed by the EPC contractors. So some examples, EPRI, VGB, etc. But very often we see that those standardized monitoring programs do not match with the programs that you should use in your power plant, because you have to really adapt them on your specific needs and requirements and your local design. And this year, for instance, we encountered a few cases where severe boiler damage has been occurred due to a mismatch between the installed monitoring programs and the programs that you should use. So if this circle is representing a water steam cycle with its 4 segments, condensate, feed water, steam, and boiler water, then what I want to know is the big question. What I want to know is in fact how I can protect my high capex components, especially when they are exposed on high temperatures. So that's the reason why most of the parameters I like to know are situated on the left side of the circle. So the boiler water side and the steam side, where you find the boiler and the steam turbine. So, but I want to be a little bit more vigilant, and I want to see upcoming chemistry incidents much earlier than that. So what I have to do is different. So you can see this is a totally different pattern. We are analyzing much more in the feedwater side to work in a proactive way to in fact detect issues much earlier. So that's the reason why we recommend to take an anticipative approach and to locate at locations that is sometimes that can sound strange to operators or non-chemists, but we like to take a very conservative attitude. So now, as my monitoring strategy lined on flexible operation, I think that a lot of you are working in a high flex operation. So again, the international standards as EPRI, VGB, IAPS, and there are so many others, are delivering state-of-the-art guidelines. And if they are adapted on your local needs and standards and design and whatever, you have already done a very good job. But the problem is that those monitoring guidelines do not care about the quality of your measurements. So if you run in a high flexible operation, you can see that your online monitors will not be fully reliable in a startup phase or in shutdown periods. It's quite difficult to fully rely on your measuring devices. So we are a little bit in a conflict situation, and that's the reason why we would highly recommend to reassess your cycle chemistry, in fact, to compensate for that poor startup monitoring. So that means that it can be interesting to work in a more conservative way and to consider additional chemistry treatments to face that the lack of reliable instruments during startup. So now, how to keep an eye on your corrosion? What is the mission of a chemist? The first mission of a chemist is in fact to set up an excellent treatment program and to have an eye on the purity of the cycle. So, but even when you have an excellent treatment and your purity is excellent and you have excellent KPIs, it can still occur that you have corrosion. So that is what we encounter the more and more due to flexible operation, that we still have corrosion even when the chemist is doing his very best. So, but how can we find a solution if corrosion products are not measured in a professional way? So, in fact, we would like to make a call to in fact reinstall first-class online, offline corrosion product measurements. In fact, to make an inventory more easy, and to finally to see what kind of additional treatments that could be implemented. So some examples are film-forming substances, alkalizing amines, dispersants, and so on. That could be implemented to face your problems during your flexible operation. So, all right, if there are questions, free to.
Yes, thank you very much, Alex. We have two questions currently from the audience. So the first one is to increase pH in HP drum, which is better, caustic closing or TSP? We follow AVT as of now.
Yes, in an HB drum, it's better to avoid alkaline products like caustic soda or phosphates because the risk for carryover is much higher than in a low pressure drum or an IP pressure drum. So you only inject that kind of products when it's really necessary. It's of course also pressure dependent. This is something to assess whether it is whether it has added value or not. But if you need to inject caustic or phosphates, the decision can be made on the fact if you run on seawater-based cooling condenser or not. So if you have a seawater-based condenser and you have condenser leakages, it could be more interesting to use caustic soda because it's more powerful to increase your pH than phosphates. But of course, caustic soda has also disadvantages. So it's a consideration to make. And another consideration can be the staffing of your organization. If you have a good staffing with a lot of people and on site, and the people are daily on site, then you can consider caustic soda, because caustic soda is so powerful that when you have an overdosage, that you can create caustic gauging in your steam path or whatever. So to conclude my answer, first you have to consider if it is necessary to do something in your HP drum. If yes, then you can choose for caustic soda when you have a seawater cooled condenser, or when you have enough staffing to follow the dosing. If not, we recommend to dose phosphates.
Thank you very much. The next question we have is a question that they were asked by the direct customer. Could we inject ammonia at condensate extraction pump? Is that okay?
Is in or in the
Could we inject ammonia at condensate extraction pump? And is that okay?
Yes, of course. So, but of course you must be careful to inject upstream your pump, because then you can be in a vacuum situation. So normally it is injected downstream your condensate pump where you have pressure. So this is mostly done, I think, in 90% of the cases. Ammonia is dosed downstream the condensate pump. But yes, there are applications where it is dosed in the vacuum site. But you must be very careful, of course, to keep a good control of your pH when you're dose it and upstream your condensate pump. But in general, of course, it is okay to dose ammonia in your condensate system.
Okay, thank you very much. Well, we have more open questions, but I suggest we address them at a later stage. Maybe you contact us, so we'll see what we can do. We'll now pass on to the next thematic that you are going to present, Marnix. And it relates to the question, are the online and offline measurement results reliable?
Yes. So the reliability of those analyzers is dramatically increased, in fact. So power plant chemists, and not seldom from my age, unfortunately, and with my experience, there is some doubt about the reliability of online instruments. And so the sensor that you see on the slide is a conductivity flow-through sensor I worked with in the beginning of my career. So you can see that there has been some evolution in the past decades. So the graph that you see is not more than the relation between time and reliability of monitoring instruments. And you can see in 1980, let's say 40 years ago, that the reliability of offline instruments, so your laboratory work, was more reliable than the online monitoring devices. So that was justified in that time to focus on your laboratory, and that your staffing was most of the time present in the lab to do analysis. But 20 years later, the reliability of the online instruments increased more and more, and then it was only the offline instruments were only used to do a double check or a cross check of your online measuring devices. So, and then nowadays we can fully rely on the extreme reliable online devices, and they are also very well adapted on our needs. So it's there is really no need to spend a lot of time in the laboratory. So this is also a call from our side to shift away from the lab to the process, and from offline to online instruments. So I would say that a plant chemist nowadays, when the plant chemist is spending most of his time in the laboratory, that he or she is maybe not that efficient, and so we prefer to focus on on activities in the process, in the control room, etc., etc. So what is now the importance of a good communication? So you have to know that chemists are working in a very low ppb range. So 1 part per billion is not that easy to measure. So those are units that are well known by chemists. But in fact, we see more and more that the online instruments are managed by INC, so by the instrument experts. So the purchasing, calibration, maintenance is performed by another service. So it's very important that there is a good communication and correlation between the activities done by INC and chemistry. So, and we see very often in power plants that the ownership is not well defined, and that it is somewhere in the cloud. So you can also say for INC and chemistry, in fact, they are not speaking the same language, and they are looking at a different way at measuring devices. And on top of that, you have also the relation between chemistry and operations. So it's very important that there is at least a daily presence of a chemist in the control room to correlate the chemistry results with eventually operational events and so on. So I can say in my 33 years of career, I had the opportunity to do a lot of root cause analysis of chemistry incidents. And yes, you can say that most of the time it's due to a monitoring issue or inadequate follow-up of alarms. But in fact, when you go deeper and you dive deeper into the incident, you will see that communication is in most cases the root cause and not the technical aspect. So that's the reason why I also want to make a call here to well define the ownership of the online analyzers. And there is a very frequent communication and reporting between operations and chemistry. So how can we solve that problem? That is, for instance, by training. So I think it's very useful and recommended that INC staff is well trained and has basic knowledge of the chemistry of a water steam cycle. But it's also the same for operators. When you don't speak the same language, you will create chemistry incidents. So this was the end of my presentation, or if there are questions on that question or the question before.
Well, thank you
Go
again.
ahead.
Well, this question has triggered a lot of reactions, so quite a few questions. The first one is for you or the experts around the table to answer. Does minimizing the offline measurements mean reducing the frequency, or does it completely remove certain tests?
Well, this is a little bit, you can interpret that question in a different way, but in my opinion, it's better to remove and to discard your offline measurements as much as possible, so you can focus on trending, making trends. When you make trends of your online analyzers, you work in a proactive way, and you will see upcoming incidents days, weeks, or months before you have the incident. So when you do offline analysis, you do only a snapshot for once a week, once a month, once a day. So this can only be a check, a quality check of your online analysis. So, and if we know nowadays that those kind of analyzers are extremely reliable, I don't think that it is necessary to do a lot of checks. Only for iron and copper and things like that, where you don't have the possibility to do it online, of course you have to analyze offline. And so regarding the frequency, it depends a little bit on your own needs, in fact. But yeah, if you do offline analysis to check your onliners, I'm not so very, I don't find it so okay to reduce your frequency, or you do it in a frequent base offline, or you discard your offline measurements. That's maybe okay.
Okay, thank you. Next question was, what is the best thermal fatigue prevention method or methods on HP economizer?
Can you repeat that?
What is the best thermal fatigue prevention methods on HP economizer?
Yeah, this is maybe not really monitoring related, maybe something for the materials experts.
This is more operation. Yeah, this is more related to operations, and I think there you have to focus on the pressure variations more than on the chemistry variations, which can occur in some types of CCGP plants. Maybe this is a topic we can take on another call or another subject, if it's related to really an incident that happens in one of the power plants.
Sometimes also design modifications can be made in order to prevent thermal fatigue degradation of the economizers.
Thank you very much. Next question is, because of very high purity water, it requires specific pH measurement. What are your recommendation of type of pH measurements?
Yes, for pH measurements, we recommend to use a separated glass electrode and reference electrode. So we don't like very much the combined electrode systems. So you need also a high flow through of potassium chloride through your reference electrode. So, and if you, yeah, of course, I cannot speak very much in terms of brands, but the most used pH meters that we see worldwide are from Swan or Yokohama, in fact. So normally, calibration of a pH meter weekly is recommended, but it depends also on the biological load of your cycle. It can happen that you have traces on organic products that are polluting your pH electrodes, and depending on that, it can be interesting to calibrate weekly or monthly. Depends on the situation.
Okay, well, thank you very much. Again, there are many more questions, but time is up, unfortunately. So we will take note of those questions and get back to you in the coming weeks or days. Thank you very much, Marnix.
Thank you to all.
Our next speaker, while he's coming over, I will present him, is our colleague Anthony Seneca, and he will answer the last two questions of this webinar. The first one being, have optimal alarm thresholds been set?
Hello, everybody. So we'll deal two questions. Now we have a good treatment strategy and we know how to monitor the chemistry. We have the questions on the threshold of alarms. So we need to achieve a right balance within those thresholds, because we have two situations, two extreme situations. We can be on one side too relaxed. That means that the chemistry will be forever okay. You will never have any alarm. And so you will not detect any upset conditions in your chemistry. On the other side, you can be too strict, and then you will have a lot of alarms in the DCS, an overflow of alarms. That means that in the end, your operators will not look at those alarms anymore. And maybe those alarms will be disabled. So in the end, we have no control over your chemistry, which is not the target. So in order to achieve the right balance, to find the right specifications, we advise to use appropriate specifications, and especially a starting point to use the internationally recognized guidelines, such as the VGB, the EPRI, and as also guidance, the IAT. This is a starting point, and you need to adapt this to your plant-specific design, which is really important to have an optimum chemistry program. So this is for finding the thresholds, but then you need to use those thresholds. And so what to do when there is an alarm? So after situations, you can do just nothing. You are not reacting to the alarm. You can call the duty guys at night, even stop the plant as a worst case scenario. That's why we need different alarm levels to indicate the severity of the fault. This is the graphic on the slide. So we like to use 3 alarm levels at Laborelec, from 1 to 3, and we associate a framework, a time frame to react to those alarms. Alarm level 1 is not a very bad thing, so you can react within a week. Maybe a slight deviation on the measurements, it's not a big issue. But on the alarm level 3, it's a major issue, and it's really threatening your plant integrity. So you need to shut down the plant if you cannot find a solution very quickly. Special attention on this point is the startup. Why? Because during the startup, we know that our measurements are not always reliable. You need some time to get the sample, you need some time to rinse the analyzer, and so the chemistry will be bad during startup. But you may have a lot of alarms because your thresholds are generally fixed in the DCS, and so you get a lot of alarms in the startup which are not reliable. So it's preferable to use some relaxed guidelines if applicable to your plant. During the startup, you don't get this overflow of alarm, and you can really spot a normal situation from this point. So this ends the first part of my presentation, my first questions. Can jump now to the Q&A.
Thank you for that. There are currently no questions from the audience. Sorry, I spoke too quickly. There is one. Are there any specific guidelines for solar plants? We have a startup shutdown every day, and sometimes during the same day, we can have 2 startups which disturb the chemical quality of water or steam cycle. It is very difficult to reach the normal value established by ST supplier or EPRI.
Yes, so this is also the problem of a lot of CCGT plants that are running on a high flex mode. Then we know that you have a lot of difficulties to achieve the steam purity guidelines. That's not a big issue. If in the past you have operated on a normal way, let's say a little bit of base load, then you can achieve those guidelines. That's already good. Then on a high flex mode, you have to focus really on the condensate and feed water train. If you have some good water inside those systems, in the condensate and in the feed water, then you may also have this good purity coming to the steam turbine, because in between you should have no pollution coming in. So that's the point. Focus more on the cold areas. When you have most of the time a sample available, as long as your extraction pumps are running, you should have a condensate sample, so you can analyze this water. If this water is good, then it should be okay in the steam system. This is not the best position, but it's a compromise.
Yes, also, if I may begin, interesting during startup that you only focus on 2 parameters, as you say, Anthony, so pH and cation conductivity, and so that it's very clear for the operator when he has to start up during the night that he only has to focus on 2 parameters, so pH, cation conductivity of your condensate train and your feed water train, and all the rest can wait until the chemists are there or whatever. So I think it's very interesting to make a very simple strategies and procedures for the operator to follow the chemistry during startup. That is not too complicated.
Thank you very much. Next question. Well, this time there is none from the audience, so I will ask you one of my questions. So could you tell me in practice which design elements have an impact on alarm thresholds, and can you give specific examples?
Okay, so typically what is not addressed during construction of a power plant is the equation between the boiler and the condenser. So generally the EPC will give you guidelines to protect the boiler, but they will not take into account the presence of an air-cooled condenser, which requires a very high pH, around 9.8, to be protected against flow-accelerated corrosion. Other examples, if you operate cogeneration plants, then you send steam to a client, you again return condensate, and you may have to adapt the treatment to take into account this. It's 2 simple examples, but quite often encountered.
Thank you very much, Anthony. I suggest we pass to the next question. The last question of our session, and then we'll have a wide open Q&A. So are there clear procedures in place for prompts, if possible, appropriate reaction.
So this last question is very important. We have defined all the steps to address the water stream cycle chemistry in a good way. And then in the end, what happens when there is an incident? That's the big question. So normally we can detect the upset conditions in an very easy way because we have some good monitoring, we have some good thresholds. So when there is deviation, we should be able to react. But what to do in case of deviation? The classic answer number one is, okay, this is an INC problem. We'll see later. It's not my business. And second answer is, I will call the chemist, when you have a chemist, of course. Yeah, the first answer is, you are taking no action, which is not very good. Second action, it's okay, but during the day, this is good, could be a good answer, but during the night, during the weekend, then you may take also no actions. So you need to have a systematic approach for the chemistry deviations. Typically, first point is to validate the measurement. It's always the same thing. Validate them. If the measurement is confirmed, then you have to identify the issue, evaluate the severity versus what I've said before, so the alarm level, and then to plan and act. And one important step, which is often overlooked, is the reporting step. It's the continuous improvement of the chemistry in the plant, is how to get the experience from the process. And also a small tip, generally when you just have one analyzer deviating, it may be in fact an INC problem. So, okay, but when you have several analyzers in alarm, then this is a real chemistry issue. So then you have to really react. And to illustrate this point, I'll show you a use case. So this is some training from a power plant. So you can see here a rise of cation conductivity in process at midnight. So not a very good time frame, but okay. This is validated by a check of the analyzer. So there is really an alarm. So what has been done in the plant? Some basic troubleshooting. You look at the cation conductivity also in the drum. So you can see it is increasing in the drum, but it stays flat in the steam. So, okay, first opinion, this is a small condenser leakage. Okay, ICC in the condensate, also in the drum, steam still okay. So we'll just open the blowdown and maintain the situation. Well, could be okay, but when you go a little bit further into chemistry, you can take a look at the pH. pH is also increasing, which is quite strange when you have a condenser leakage. You should expect a pH decrease. So, okay, this is an accumulation of caustic elements. This is not a condenser leakage. This is a leaching from the Demin plant. And in fact, what is the action that should be taken when there is such an incident is to close the blowdown. Why? If you open the blowdown, you allow more contaminated Demin water to enter your cycle. This is not a good thing. So take care. The wrong actions are counterproductive, and you need to set up some procedures to have a detailed structure for the troubleshooting, and not just stop at the first element to say the situation is under control. That's not the case. And a last point, you need to take the right action, but also in a prompt way. The fast response is really a key. This is another example. This is a real condenser leakage for this case. It was a massive leakage that occurred during a restart of a combined cycle seawater cooler. So during the restart, there was an increase, a surge of the parameters in the condensate from the extraction pumps were turned on, from the sodium and the cation conductivity. This is a log scale. And the plant has been turned on. During 5 hours, the plant has been operated with such chemistry. This is not very good. There was 6 weeks of downtime for rinsing this plant, and then the LP steam turbine rotor has been replaced. So again, some downtime, a lot of cost. So the problem was detectable really from this, even before starting the plant, from the extraction pumps being turned on. And really, one point is you have to dare to stop a power plant if needed. For running 5 hours, this has cost months of downtime and millions of damages. So this will end my presentation, and you can go to the Q&A session.
Thank you again, Anthony. I don't see any questions from the audience at the moment. So in the meantime, I will jump in with my first question. In case of an alarm or an upset, could you give us practical examples of actions that have to be taken? And this in typical situations?
Yes, typically the first point is to validate the measurement. So nowadays, with a lot of instruments that are installed in the power plants, the easiest way to validate the measurement is to perform some cross-check. So just look at several at the other measurement at the same type, at different catenary conductivities without deviating. If you cannot do a cross-check, you just go to the sampling station, you check the flow rates, you take the analyzer, for example, the saturation of the resins. Then if it's validated, you have to perform this basic troubleshooting. You can have some decision trees in the DCS. If you have a condenser leakage, it could be very simple actions to really look for the sources to operate on a half condenser to check what is the leaking water box. You can plan for actions. So it's very plant specific. We can have general guidelines, but then you need to customize this to your plant design.
Thank you. I still don't see any questions specifically for you, so I suggest we jump back into questions that were previously asked. Well, you go and join our panel of experts. The first one, and I hope I can interpret it right, Ali, what is the reliability of chloride analyzer seawater cooling condenser for a CCPP? Does that make any sense to anybody?
Well, yes, the chloride analyzers are not used that often in the power industry because of the reliability and the availability. So it happens very often that you have problems with that kind of ion selective electrode systems. But of course, we are also very interested to know your feedback if there is any on the reliability. I've seen it a few times in power plants, and it seems to be that reliability is not higher than for sodium analyzers. So, but anyway, we stay very interested to have also your feedback so that we can do something with that. And but for the moment, we don't have the information that chloride is more reliable than sodium.
So there's a good compromise, economically speaking, that sodium is the preferred alternative for the moment.
Okay, thank you very much. Our next question from the audience is, what kind of automation is available today to minimize the operator intervention for drum boiler water chemistry deviation?
Well, for automation, when you have a deviation, we, especially in a drum chemistry, I think it's maybe not the preferred way to automate everything, because you need to keep a human eye on the situation. If you have a deviation, this is not a normal situation. So something is going wrong with your chemistry and you need to troubleshoot the problem. Going the automated way, okay, you can stabilize the chemistry with some automated blowdown, for example, but it will not address the source of the pollution, which is very important. You need to address the issue, not really the symptoms.
Thank you. Another question from earlier was, we found sodium remnants in condensate water. What could it have originated from, according to your experience? Tricky one.
It was sodium and that sodium?
Remnants. Probably need more detail regarding.
Without details,
yeah.
It's difficult to say, of course.
Okay, so Gerard, if you can complement your question or detail a little bit more, and in the meantime, we will jump on to another question. What would be the desired oxygen level in boiler field water with a minor chloride presence, say approximately 100 ppb?
100 ppb of chloride, that's very high. That's not a common way of operating the plant. Then you need to stick to the guideline. But you're already with 100 ppb of chloride, you're in a quite elevated alarm level, so really it's not a safe way of operating the plant. You have no choice, okay. Then you need to go quite low on the oxygen, so it will be in something like below 20 ppb should be acceptable. Stick to the guidelines. Okay,
thank you. Well, another question is, can we detect condenser leakage by testing chloride? We currently don't have sodium analyzer. And what is the limit?
Yes, to detect the condenser leakage by offline analysis is maybe not the most recommended way to do, because when you do offline analysis of chloride, it's already heavy and tough to have reliable results. So we really recommend to automate your condenser leakage system, and that on at least an online analyzer is installed, because from the moment that you have a condenser leakage, you start corroding your system. So you have to react immediately, and you can never do it by offline analysis. You will always be too late, in fact.
And the cation conductivity is also a good solution if you don't have a sodium
It
analyzer.
will work. It's less sensitive than a sodium analyzer, but it will work indeed.
Next question, and I hope again I interpret this properly. Is HRSG preservation with ammonia and under nitrogen capping and DO measurement acceptable? Meaning by that we are considering without hydrazine addition.
Yeah. Yes, it's recommended until a certain level. It depends also on the time that you will be in shutdown. So you can always create standstill corrosion. It depends also on the pH that you apply. If you apply an extremely high pH, like 10.5, you will it's okay. It's definitely okay. But when it's a pH of 9 between 10, you must be very careful if you have a long-term shutdown to keep the situation like it is. So to be conclusive, according to us, this is a tolerable, justified situation for a short shutdown, but not for a long shutdown. And then maybe the question can be, what is short and what is long? And we can discuss hours to find a solution on that. But let's say when it's an order of magnitude of weeks, that it is tolerated to apply such like situation.
Okay, perfect. Thank you very much. Time's up apparently. Sorry, I was just taking the time. So I would like to thank all of you for your presentations and your answer to all the questions we received, as well as all our speakers for as well as all our audience for the questions that you send us and for listening to us. We will send you shortly the presentations that were given today, as well as an attachment which are practical slides to take away with lesson learned. You can contact us at any time at chemistry.laborelec@engie.com. Oh, there you are, so you can see it. I hope you enjoyed the webinar today. If you have any additional questions, do not hesitate to send them to us. Do not hesitate to send them to us. Our experts are always available and ready to help you in case of needs. And last announcement, but not the least one, we will have on the 12th of December our next webinar. Please feel free to attend. The meeting request will be sent shortly. The title of this webinar will be How to Better an SCR DNOx Strategy and How Could It Save You About $1,000 a Year. Once again, thank you very much for joining us. And $100,000 a year, sorry. I was getting weird looks, understandably. Well, thank you very much again for joining us, and hope to hear from you soon again.